Okay, so let's go into some more of the anatomy of springs. Remember on the last video, I defined two things. I said that the work for a spring is 1/2 kx squared, kx squared, there we go. And that the force from a spring, I'm going to drop the negative, is kx. We're going to let our forces define for us what direction or what sign that would be. So let's see what I have going on here. This is like the elevator question. If you back yourself up a little bit, when we were first on elevators weighing ourselves, and it's accelerating up and it's accelerating down, and then we looked at the forces between this, and we said, okay, so I can kind of look at this two ways. I can say that there's a normal here, which there is, and then I have gravity acting down. Or I can kind of look at this as the interaction between this top of the spring scale that's beneath my feet and the spring itself. So I have like this action reaction going on here. Well, this would be the exact same picture if I was standing directly on the screen. The board between the spring and my feet doesn't have any impact at all. It's just letting me stand there without wobbling. So spring scales, that's how they work. They have really strong springs in there. And what the scale is actually measuring is the distance of compression. And then that reads out, oh, you can't see their eyes, they're happy. That reads out, now they look evil. Okay, I'm leaving the drawing alone. That reads out your weight. Okay, so let's think about what the forces are. I have force of gravity down, which is the 600 newtons. And what's pushing back up then is I have compressed that spring some amount. So if this thing has come to equilibrium, when I do my sum of my forces in the y, let's see, I don't know, let's just go up as positive, will be rather standard. So my forces in the y then become the force of the spring minus the force of gravity. It stopped moving. I'm in equilibrium. I compressed it. I'm not bouncing up and down. It's staying still. So this whole thing equals 0. Then what I get? I get the force of the spring equals my weight. And my force of the spring is this kx equals the force due to gravity, mg. And as I'm writing it, I'm like, I gave it to you in 600 newtons, so we didn't need to do that step. I know how much I compressed it. So k equals my weight. I'm going to go my 600 newtons divided by this 1 centimeter. So let's write this a different way. There are 10 centimeters in a meter, so 10 to the negative 2 meters. That's 1. So divided by 10 to the negative 2 meters. Now I can turn around and go, so k is 600 times 10 to the second newtons over meters. That's the units of k. So what does k tell us? K just tells us how strong a spring is, how hard or easy it is to compress or stretch. And this one here, that's a pretty high K. So that's a pretty stiff spring. And you think about it, with people stepping on them, you don't want it to compress much. You want small compressions to be what the scale is going to read, and not these massive like dips. You'd have to have a huge space to have a scale otherwise. So that's what this is. That's all K tells us. So the force constant for the spring, this letter K, tells us how stiff the spring is. Notice I didn't use any negative signs in here. My K is the amount it's compressed or stretched. I've already done my sum of forces. I've already worried about whether or not it's positive or negative because that's dependent on how I've defined the direction of positive or negative. So it doesn't matter. The amount it's compressed, well, that'll be the amount that it's going to stretch out in the end anyhow. So I guess if I wanted to, one of the things I could have done is left the negative sign in there for the kx, and then done the x being starting at 0, and then therefore I'm getting a negative number to get a positive value in the end. I can do that, and that's totally fine if that's what you want to do. Or you just kind of think of it in terms of what we've already done. We've defined positive and negative direction. So this is just going to be the total amount of compression from equilibrium. So if it compresses 1 centimeter, that's what it's telling you. That's how much it compressed from equilibrium. And that's all the information I know. I need. I'm going to take my kind of alien-looking drawing and move on.